everyone. Hello. I want to make a quick video on Stokes Theorem. I'm also going to put up a text of me, or actually a PDF of me just working a couple of problems from the book. Basically, if you understand Green's theorem, that was 5.4 I believe, this just brings it to a higher dimension, a second higher dimension. And so in this higher dimension, it's called Stokes Theorem. And so Stokes basically, I guess, took what Green did and just took it to a new level. So this is used in physics and in mechanics, fluid flow, things like that. So if you have to take those types of classes, you may see some of this or some form of this. So what is Stokes Theorem? It gives a relationship between a surface integral over an oriented surface S. So we have some surface S up here, not the whole figure, just a surface, and a line integral along a closed space curve C forming a boundary of S. So you see this is C down here, and there is a region there, but it's also, this is C just brought up to the figure. So, and that's a closed, a smooth curve. The positive direction along C is a counterclockwise relative to the normal vector n. So it's counterclockwise. You see our normal vector n. It's positive because if we wrapped our thumb around it, then our thumb would be pointing up, just like in physics. But what is Stokes Theorem? Stokes Theorem is actually, it can be done with a line integral, but at times that can, if you remember doing line integrals where you had to do the parametricization, that can get a little tricky to figure out all the parametricization of the smooth curve C. So it is equal to f dot dr, but it's equal to the double integral over the surface of the curl of f, so hopefully everybody remembers how to take the curl, dotted with n, the normal vector, the unit normal vector, ds. Okay, and this says, note that the line integral may be written in differential form, where we have the m dx plus n dy plus p dz, or in the vector form. And so this is f dot t, this is that tangential vector ds. So I'm going to go through, I believe I go through example 1, just showing you how to use Stokes Theorem to find the answer in the PDF. What you also need to understand is, and this is just going through the work, and this is the way we have to handle that normal vector. And notice we have just k here, so anyway, you can see G up here and figure out how to find your I, your J, and your K, and all that kind of stuff. But notice as we go down here, we do have to transform this over to dx dy or dy dx so we can get some boundaries. And then sometimes it's better to to take it and change it into polar or something like that. But here it was easier just to use dy dx as our dA. Okay, and then got the answer of -9. Now here's what I'm talking about. You could do it with a line integral, but you have to figure out these paths, and the parametricization is kind of hard to do, but you would have to figure out the paths, what would give you the points between t equals, and t could be anything, but here they chose 0 to 3, 3 to 6, and 6 to 9, and you would get the points that you're supposed to get. And so they go through and they do the line integral and break it up into, since there's 3 parts here, you have 3 line integrals, and they break it up and they get the same answer. So so that just means that the line integral will give you the same answer, but usually, even though it may look like a lot more work, it's really easier to use Stokes Theorem to do this. And so just to give you another visualization of Stokes Theorem, I went ahead and went to Paul's notes. And again, he just says the higher dimensional version of Green's theorem. Um, and it says around the edge of the surface we have a curve C, just like on the other. This curve is a boundary curve. The orientation on the surface S will induce a positive orientation of C because it's going around this way. To get the positive orientation of C, think of yourself as walking along the curve. When you walk along the curve, if your head is pointing in the same direction as the normal vectors, while the surface is on the left, then you're walking in the positive direction of C. Alright, and then they go through the same thing. They tell you that let S be an oriented smooth curve that is bounded by a simple closed smooth boundary curve C with a positive orientation, and let F be a vector field. Then the integral over C, the line integral of F dot dr is equal to the double integral over the surface of the curl of F dotted with ds. In this theorem, note that the surface S can actually be any surface so long as the boundary curve is given by C. Alright, this is something that can be used to our advantage to simplify a surface integral on occasion. Alright, and we didn't do the surface integral sections, we just didn't have time, but I mean they're just integrals along the surface and getting normal vectors and all that kind of stuff, so it's not that big of a deal. Alright, so it says use Stokes theorem to evaluate the curl of f dot ds, where this is our vector field, and S, the surface S, is the part of z equals 5 minus x squared minus y squared above the plane z equals 1. And assume that S is oriented upwards. Alright, so we're walking around that direction there. And this is at z equals 1 up to 5, because if x and y were 0, it would be at 5. Alright, so there's the sketch. In this case, the boundary curve C will be where the surface intersects the plane z equals 1, and so the curve will, and so will be the curve. We have 1 equals 5 minus x squared minus y squared. Alright, or x squared plus y squared equals 4, bottom there, at z equals 1. So it's just a circle there. So not too hard to understand. It's a circle. Alright, so the boundary curve will be the circle of radius 2 that is in the plane z equals 1. The parametricization of this curve is, so they do the parametricization and figured out that this is the path, and that's where t is between 0 and 2 pi. Alright, let's see. The first two components give a circle, and the third component makes sure that it is in the plane z equals 1. So we have that right there, and this is just a circle. Okay. Using Stokes theorem, we can write the surface integral as the following integral. So the double integral over the surface, the curl of f dot ds, is equal to f dot dr is equal to, and here they're just working out their stuff, and they're saying the integral from 0 to 2 pi, and we have, this is that function, remember, where you have to change the vector field into terms of t. So here's where you take the equation of the vector field and you change it into terms of t. Alright, and dot that with dr. Alright, and so they worked through that. They figured out what f in terms of t was. They found out what dr was. There's r, or dr, derivative of r. And then here's f dot dr. Okay. And so it says now we can do the integral. The curl of f over s dotted with ds is equal to the integral from 0 to 2 pi with negative 2 sine t minus 24 sine t cosine squared t. They worked that out and they got 0. Okay. And so here's another problem working with Stokes theorem. If you want to look through it, you know, this to me looked like they used more of the line integral stuff. They didn't use they really didn't do much of they did Stokes theorem, but they said Stokes theorem is equal to the line integral, and then they did the line integral instead of doing actual Stokes theorem. This one to me looks like they're actually using Stokes theorem because they find the curl of f. And so the one that I work out for you in the document that I'll put right below this video, I use Stokes theorem to work it out and do the curl of f. But this is a good example. You know, these are good examples to look through. So you might want to look through this, and then of course there's always good examples in the back of the section that are odd that you can get solutions to at calcchat.com. There was one other thing that I wanted to mention, this physical interpretation of the curl. This could be used in fluids, and it says, let me just read through this real quick. Stokes theorem provides insight into physical interpretation of the curl in a vector field F. Let S sub alpha be a small circular disk. So this is the disk S sub alpha of radius alpha, centered at XYZ with a boundary of C. And you can see it is going in that counterclockwise rotation. It says at each point on the circle C sub alpha, F has a normal component, F dot n, and then it also has this tangential component, F dot t. It has the tangential component, that's the tangent vector, t, and then we have F dot t. So a fluid tends to move along a circle rather than across it. Consequently, you can say that the line integral around C sub alpha measures the circulation of F around C sub alpha. So if we did the line integral over C sub alpha of F dot t ds, that would be the circulation of F around C sub alpha. Okay, and then down here it shows you that Stokes theorem says, well, we have this double integral and we have these constant values right here. If we take those two out front, curl of f dot n, all that's left over is the area, and that's pi r squared. This double integral stands for the area. So that would be the curl of f dot n times pi r squared. So you'd be able to do it without actually using calculus. You just have to do the curl of f and find the unit normal vector. And so you might want to read through some of this about the rotation and everything, and then there's another application of the curl here that's shown. I mean, this is in your textbook. This is more physics and more kind of getting into fluid flow. That would be like Engineering Mechanics 3. So I made sure all the problems that I assigned had videos with them. I noticed some of you have already completed them, already made hundreds on them. So if you need me to work out a problem or try to explain something, I will do my very best to do so. If not, this is the last section we're going to cover, so we'll have our test and our final next week, and I will be getting you more information about that out on Monday. Thanks. Have a great day. Hope everybody's safe. Send me emails if you have any questions.